1905. Albert Einstein was working through his equations when he stopped. The numbers were pointing at something. A point where space curves infinitely. A point where gravity climbs without limit. A hole of darkness from which not even light escapes. He shook his head. This cannot be real. He did not believe the result, did not believe the monster his own theory had predicted, did not believe the thing his own equations had created. But the universe did not care what Albert Einstein believed. In 1905, Einstein published the special theory of relativity. 10 years later, he completed something far more ambitious: the general theory of relativity, a set of equations showing that gravity is not simply a force, it is the curvature of space itself. The first person to fully solve those equations was not Einstein. It was a German physicist named Karl Schwarzschild. He solved Einstein's equations in a trench on the front lines of the First World War, while artillery shells flew overhead. And he found something. If enough mass is compressed into a small enough space, a special boundary forms around it. Beyond that boundary, nothing, not even light, can escape. Schwarzschild sent his result to Einstein in a letter. Einstein's response was simple and direct. I do not believe this can actually exist in nature. The man who created the theory refused to believe what his own theory had predicted. That is where the story of black holes begins. The greatest physicist in the world, unable to trust his own equations.
The event horizon. The name carries its meaning perfectly. You cannot see beyond a horizon. You cannot know what happens on the other side. And once you cross it, you cannot come back. The event horizon is not a physical wall. You cannot touch it. There is no hard surface. If you were falling toward a large enough black hole, you would feel nothing special at the moment of crossing. You would simply pass through. But from that moment on, every direction in the universe changes. In ordinary space, you can move in any direction: forward, back, up, down. You have choices. Inside the event horizon, every direction points toward the center. There is no direction that leads out. Even traveling at the speed of light makes no difference. Space itself is flowing inward, and you are moving with it. You may have heard of escape velocity. To escape Earth's gravity, you need to travel at roughly 11 kilometers per second. Jupiter requires more. The Sun requires more still. At the event horizon of a black hole, the escape velocity equals the speed of light. And nothing in the universe travels faster than light. That is the definition of a black hole, the place from which light itself cannot escape.
Now we reach the strangest part of the story. Imagine you are near a black hole, just outside the event horizon, deep inside an enormous gravitational field. Your time flows normally. Your heart beats, you breathe, your watch ticks. But to an observer watching you from far away, every movement you make appears to happen in extreme slow motion. This is what Einstein's general theory of relativity predicted. The stronger the gravity, the slower time passes. We call this time dilation. This effect is real, even here on Earth. GPS satellites orbit where gravity is slightly weaker than on the surface, so their clocks run microscopically faster than clocks on the ground. Without correction, this would cause position errors of several kilometers every day. Near a black hole, the effect becomes extreme.
If you were watching someone hover just above the event horizon, they would appear frozen there forever, growing dimmer, growing redder, never quite crossing the boundary, as if time had stopped for them entirely. But for that person, nothing unusual happens. They simply drift across the horizon without feeling a thing. The same event, two completely different experiences. That is the heart of relativity. Time is not absolute. It flows at different rates depending on where you are and how strong the gravity is around you.
Now, consider what actually happens to something falling into a black hole. The first thing you would feel is a difference in gravity. A black hole's gravitational pull is so extreme that your feet, being slightly closer to the center, experience significantly stronger gravity than your head. That difference pulls you vertically. It stretches you. At the same time, gravity from all sides converges toward the center, compressing you from left and right. The result is that you are stretched lengthwise and squeezed sideways, like a strand of pasta being pulled thin. Physicists call this spaghettification. It sounds like a joke? It is not. It is the correct scientific term. For a small black hole, this tearing effect begins far outside the event horizon. You would be stretched apart long before you reach the boundary. For a supermassive black hole, billions of times the mass of our Sun, the tidal difference near the event horizon is relatively small. You could cross the horizon without immediately feeling it. But as you approach the center, the process becomes unavoidable. The tidal forces grow, the stretching intensifies, the compression tightens, and finally, the singularity. The point where the mathematics returns infinity, where the equations of physics refuse to give an answer. What happens there? We do not know. Einstein did not believe in the monster his own equations had created. But now, we know. At the center of our galaxy sits a black hole 4 million times the mass of our Sun, Sagittarius A star. In 2022, humanity photographed it for the first time. Black holes are real. Einstein was wrong. His belief that they could not exist was wrong. And Einstein was right. The equations that predicted that are still correct 100 years later. We do not know what happens inside a black hole. We do not know how physics behaves at the singularity. We do not know whether information is truly destroyed or preserved somewhere we cannot yet see. A black hole is not an answer. A black hole is a question that shows us exactly how much we still do not understand. And as long as that question exists, physics continues.